All right, so this is an addendum to the enolate formation chapter, or video. I keep calling them chapters, I don't know why. So, as I said in the last video, pKa of a single carbonyl compound is somewhere like 18 to 25, depending on, so let's do this, okay? So the pKa of that proton right there, the alpha proton, is going to be actually wider than that, 16 to 24 or 5, but depending on X, and there's going to be Y and Z here, and Y and Z, right? So that's a pretty big range, but if there's only a single carbonyl, the pKa of this proton is never going to be lower than the pKa of, say, water. All right, so even acid aldehyde, where X is an H and it's just a methyl group here, these protons aren't more acidic than water, and so in an equilibrium with hydroxide, are still going to favor the carbonyl compound. That's going to change though on here. So again, if you watched the enol video, and I hope you did, then there's these special cases where you have more enol than keto compound. Remember, up here, when there's just a single carbonyl, the enol is way less favored, like billions of times less than the keto compound. In this equilibrium, phenol, right, the ring is aromatic, and so that makes the molecule way more stable than it would be if it was in the keto form. Similarly, if the protons sit between, if you have a 1,3 dicarbonyl, so let me do the numbers here, right? So 1, 2, 3. So the protons on carbon 2, you can make the enol, and it forms this intramolecular hydrogen bond, so the enol is more stable. Well, these are also going to be more acidic. Okay, so what do I do with my eraser? Okay, so these are going to be more acidic as well. This, I said here the pKa is 10 or so, and again, depending on what is bonded here, if this is a ketoester or a diester, the pKa for these two protons is going to be like 9 to 12, say. Anyway, more acidic than water. The same thing here, depending on what is bonded to the phenol, the pKa here can be sort of 7 to about 10. So if you look at all these pKa's, 9 to 12, 7 to 10, if you take phenol and treat it with hydroxide, we get this phenolate anion and water. Okay, pKa of phenol is right at 10, pKa of water's 15.7. Okay, the weaker acid is water, so the right side of the equation is favored by about 6 orders of magnitude, or a millionfold. All right, so hydroxide can deprotonate phenols nicely. Same thing up here. If we have, what is that, 2,4-pentane dione, so 1, 2, 3, 4, 5, 2, 4 dione, so 2,4-pentane dione, and hydroxide. We get that equilibrium set up. pKa of this is also about 10. So by about the same effect, by the same margin, the right side is favored. I refer to these as dicarbonyl enolates. Dicarbonyl enolates are a lot more, they're much weaker bases. They're much more stable than a single carbonyl enolate. And so these are weaker bases, better SN2 nucleophiles. All right? Because they're a weaker base, the competition with the elimination of a potential E2 reaction is less. And so those dicarbonyl enolates are really good nucleophiles in the SN2 reaction. And again, we'll see that in the malonic ester synthesis. malonic ester, malonic acid, acetoacetic ester, something like that. Okay, next we'll do some reactions.